Hello everyone, welcome back on my YouTube channel. Today is the right time to start another part of our classes, which is entitled Classical Measures of Dispersion. And then please take your calculators, sheets of paper, take a deep breath and make yourself a strong coffee. Let's start. Why are the measures of dispersion so important? Why do we count the measures of dispersion? At this stage, we know how to find, how to indicate the average typical level of considered phenomena. This axis represents the values of our variable, and we know how to compute mean value or the middle value on the basis of the previous acquired knowledge. Alright, but now we will learn how to determine the degree of the differentiation of the variable values. In other words, we will show on average how much the variable values differ from the typical, from the average level. Let's imagine following situation. We consider two firms, firm A and firm B. These firms have different politics of the monthly wages. In firm A, which utilize the equality politics of wages, wages of the employees are quite similar to each other. Yeah? In this firm, mean of the monthly wages is somewhere between minimum and maximum value, and minimum and maximal value are quite similar. Okay, but the firm B has completely different politics of wages. Some workers are characterized by very low wages, and some employees, for example, the members of the management board, are characterized by very high monthly wages. Yeah, and maybe the mean value is the same. The mean value of monthly wages in both firms is the same, but in this firm we see that the differentiation of the variable values are much higher than in this firm. In this firm, the employees are similar to each other in point of view of monthly wages. In this firm, the employees are different from each other in point of view of monthly wages. Here, monthly wages are more differentiated than in this firm. So for statistician is very important information. Yeah, here the typical level is the same, but the situation in both firms are completely different. So it is important. This is the answer for the question, why do we count the measures of position? This is very important additional information about the considered phenomenon. Essentially, we divide the measures of dispersion into two basic categories. The first category contains classical and non-classical measures of dispersion. The second category contains the absolute and the relative measures of dispersion. In the first category, classical measures of dispersion are associated with classical measures of position that we have known before, especially the arithmetic mean. Non-classical or positional measures of dispersion are associated with non-classical measures of position, like median, like quartiles, and etc. The second division into absolute and relative measures of dispersion. The differences between the absolute and relative measures of dispersion lie in the construction of these measures and consequently lie in the units of the measurement that have been used. The units of absolute measures of dispersion are usually the same as the unit of considered variable. I said usually because the variance is the only exception here. For example, if we consider the monthly wages in the firm expressed in dollars, standard deviation of the wages, mean absolute deviation of the wages, quartile deviation of the wages is expressed exactly in dollars. Generally, we can say that absolute measures of dispersion are expressed in physical or in monetary units. So here we have a little problem here because we can't compare something which is expressed in different units. Wages in dollars and, for example, unemployment rate which is expressed in percents. For this purpose, we use the relative measures of dispersion. Here we can compare the differentiation of the observed values of different variables here expressed in different units, because these measures, these coefficients are devoid of the units. There are no units here. These measures are expressed in percents or using decimals. There is no unit here, so we can compare the differentiation between the different set of the data. For example, we can compare one attribute on variable, the differentiation of one attribute on or one variable in different populations. Like before, we have one variable, monthly wages, and different populations, different firms, various firms. So we can compare the differentiation, the spread of the monthly wages values in different firms. Or we have one population and different attributes or variables, like here. For example, we have one population, the voivodeships of Poland, and we can compare the voivodeships in point of view of different variables like GDP per capita, the unemployment rate, or the investment expenditures. Yeah, and we can compare the differentiation in one population, but in point of view of different variables, using different set of the variables. And this is the situation when we use the relative. Relative means that these measures can be compared, yes, between different populations and between different variables, different attributes. Let's start with the classical measures of dispersion. First of all, we are going to describe the variance and the standard deviation. The variance is the basic classical measure of dispersion. The variance is denoted by the symbol of s squared with the subscript of x or y or z or something else, which indicates the notation of considered variable. The variance is the sum from I equal to 1 up to n of squared deviations of the variable values from the mean. And this sum is divided by n, so it means that here we have the average square deviation of the variable values from the mean. Let's imagine this simple example, the visualization of the problem. Let's imagine this simple statistical series in which we have 3 observations, x1 equal to 3, x2 equal to 4, and for example x3 equal to 8. Okay. In the first step we are looking for the mean value, arithmetic mean. 3 plus 4 plus 8 is 15. 15 divided by 3 gives us 5. Arithmetic mean of all variable values is 5. In the first step, we are looking for the deviations. The deviation is the difference between the variable value and the mean value. So this is actually the distance between the variable value and the mean value. The first deviation equal to -2, yeah, is the distance between x1 and x mean. x1 minus x mean, it's 3 minus 5 minus 2. The second deviation is the difference between x2 and x mean. x2 minus x mean is 4 minus 5. It yields 2 minus 1. And the last deviation, is positive now, because we have the difference between x3 and x mean, which is 8 minus 5. It equals to 3. Some deviations are negative, one deviation is positive. But we are looking for the distance. We are looking for the average distance between variable values and the mean. Yeah? So the solution is to raise these deviations to the power of 2. Yeah? And in the first step, we have first squared deviation equal to 4. The second one is equal to 1, and the third one is equal to 9. Yeah? Okay, but here we have a square deviation equal to 4. Here we have square deviation equal to 1, and the last one is the biggest one, which is equal to 9. But we are looking for the average deviation, because here I have 3 different numbers. I need one synthetic measure, one synthetic value that express the average square deviation. Yeah, so we should compute the sum of these deviations. Yeah, the sum of these deviations, which is equal to 14. Yeah, and divide this sum by the population size, the number of the individuals in the simple individual series. So variance here, variance of the variable x values is 14 divided by 3. So this is 4 and 2/3. Yeah. If x is expressed in a certain unit, the unit of variance is units squared. Yeah? This is the first property of our measure. The unit of variance is a square of the unit of considered variable. If the variable is expressed in dollars, the variance of this variable will be expressed in dollars squared. So for us, for the economists, for the managers, it has no sense, because it has no economic interpretation. What does it mean if I have something expressed in dollars squared in percentage in percent squared? It has no sense. So this measure has no economic interpretation. Variance is computable for all measurable variables, and we talk about the squared values. Yes, squared values. So variance takes only non-negative values, of course, obviously. In the variance we have the squared values. If we look into the details, we notice that here actually we are dealing with the square of a difference. Yeah. From the primary school, it seems to me that we remember the short multiplication formula. Yeah, a minus b squared is a squared minus 2ab plus b squared. We can utilize this simple property in the formula of variance, and we can transform this form of the formula into that simpler form, in which we have average square of the variable values minus arithmetic mean squared. Let's back to our example in order to prove that this formula can be transformed into that formula. We need what? We need average square of the variable values. we need the squares of the variable values. 3 squared, 9. 4 squared, 16, and 8 squared, 64. Yeah? 64 plus 16 plus 9, it's 89. 89 is our sum. 89 divided by 3 is, here we have 3. Let's start with the variance. 89 divided by 3 minus 5 squared. Yes, the arithmetic means squared. It means that we have here 29 and 2/3 minus 25, and this is exactly 4 and 2/3 unit square, of course. Yeah, so it works. As you can see, we can to summarize the problem, we can use the both ways of computing the variance, the first one or the second one. Alright, and now it's the right time to prove the correctness of the previous relationship, the correctness of the transformation of the variance formula. In order to prove that, we are going to use the short multiplication formula. We can expand this operator of the sum using short multiplication formula, and we will receive the sum from I equal 1 up to n of xi squared minus 2xi multiplied by x mean plus mean value squared. And we of course divide this operator of the sum by n. In the second step, we can write down this sum of the bracket using three sums. The first sum is sum from I equal 1 up to n of squared values of variable x. The sum from I equal 1 up to n xi squared. Minus the second sum is the sum from I equal 1 up to n of 2xi multiplied by x mean. And the last sum is the sum from I equal 1 up to n of mean value squared divided by n. Okay, and we can divide the next sums by n. First we have sum from I equal 1 up to n of xi squared divided by n. Minus, here we have two constants, yes, two fixed values. So we can move these two constants before the sum, the operator of the sum. So we have 2x means multiplied by sum from I equal 1 up to n of xi divided by n. And in the last element contains the sum of n elements in which we have n elements of x mean squared. So we have n x mean squared elements here. divided by n, of course, because here we sum up n times mean squared value. We sum n times mean squared value. Okay, and finally we have what? The sum from I equal 1 up to n of xi squared divided by 2. Here we have what? It seems to be that you have noticed that here we are dealing with the mean, arithmetic mean, yeah? Because here we have the sum of all values of the variable x divided by the number, divided by the population size. So this is mean value of x. So we have 2 multiplied by x mean multiplied by x mean. Yes, this is this relationship. Plus simply x squared, mean x squared. So we have here the sum from I equal 1 up to n of xi squared divided by n minus 2x mean squared plus 1 mean x squared, and finally this is the end of the proof. We have the sum from I equal 1 up to n of xi squared divided by n minus mean x squared. Here we have the next features of the variance. The fourth feature is the larger variance, the larger dispersion. Let's imagine the axis which represents the values of the variance. The values of the variance from 0 up to plus infinity, because we know that the variance takes only the non-negative values. If our variance takes 0 value, it means that we are talking about the zero dispersion. Zero dispersion differentiation of the observed values. It means that this is the situation when all the values of the variable are the same. So, in other words, it means that there are no differences between the values of our variable and the mean value. The example 2, 2, 2, the example of the individual series. Every value in the individual series is equal to 2. It means that variance is exactly equal to 0. Yeah, because mean value is 2. There are no differences between the values of the variable and the mean value. And now in the situation when we move away from 0 to the right side, we increase the differentiation, we increase the variability of the data set. Yeah, so here differentiation increases, the dispersion increases. Dispersion rises. Okay, if all the values of variable y are linear function of variable x values in the form of that we well known, we can use the following relationship. If y is a linear function of x, then the variance of variable y values is equal to squared b parameter multiplied by the variance of x values. But b parameter is taken from the linear function here. Of course, we can use it. Here we have the appropriate example. When we talk, for example, about the temperature conversion from Celsius scale to Fahrenheit scale, where in the situation when we know this linear relationship, yeah, we don't have to transform every x value into y value and compute both variance of x and variance of y. It's enough to compute the variance of x and multiply the variance of x by squared b parameter, and we will receive the variance of y. Ladies and gentlemen, this is the most important measure of dispersion. This is the main and the most often used measure of dispersion, the standard deviation. We define the standard deviation simply as the root of variance. This is the symbol of standard deviation. This is symbol x with the subscript that indicates the symbol of considered variable. And this measure indicates, express, determine average deviation of the variable values from the mean. Let's come back to the previous example. I will show you the main idea of the standard deviation. As you remember, we consider a very simple individual series in which we have 3 observations, 3, 4 and 8. The mean observation, the mean value is equal to 5. In the first step we have computed simple deviations, yeah, but some deviations are negative, some deviations are positive. In order to solve this problem, we compute squared deviations, yeah, which are non-negative, of course, 4, 1 and 9. And in the final step, in the variance computation, we have computed average squared deviation, average squared distance between the variable values and the mean. And the average distance, average squared distance between the variable values and the mean is 4 2/3. But okay, as I said before, we don't like to operate by squared units. Yeah, squared dollars, squared percents, squared persons. It has no sense for us. So we should come back to the right units, to the appropriate units, to the right scale. So we should compute the root of this average squared distance, and we will receive the average deviation, average distance of the variable values from the mean. And we receive 2.16 units without squared, as you can see. 2.16 is the average deviation of the variable values from the mean. Yeah, here we have the value plus minus 2.16. 16. This is the average distance between the variable values and the mean. This is one unique value that describe very well this phenomenon. Here we have different deviations, yeah, but the average deviation is about 2.16, average deviation of the variable values from the mean. We have used one number, 2.16, to describe different deviations from the mean. This is the average deviation from the mean. Okay, and the properties of standard deviation are similar to the properties of the variance. Of course, we know that the unit of standard deviation is the same as the unit of the variable, so standard deviation, contrary to the variance, has its own economic interpretation. Standard deviation is computable for all measurable variables, and standard deviation takes only non-negative values. Of course, the larger standard deviation, the larger dispersion we have. Standard deviation of variable values is equal to 0 when all the values of the variable are the same, yeah? And we can also say if all the values of variable y are linear function of variable x values, in that form we can compute immediately the variance of y using the standard deviation of y using the variance of x and the module of b parameter. Yeah, if we know these amounts, we can quickly compute the standard deviation of variable y values. In the interval series, as you know, we perform using the frequencies or relative frequencies, and of course we don't know all the values of considered variable. For this reason we operate by the middle of the classes, and here we have the appropriate formulas. We will use them later, and now it's the right time to solve the first problem connected with the measures of dispersion. Task 1. CEO of large multinational company called Sadida Corporation commissioned a review of the revenues of 6 regional branches in billions euros in 2010 and 2020. The results were following. Yeah, here we have IDs of the branches A, B, C, D, and so on. Here we have the revenues from 2010 and revenues from 2020. And the first command is to calculate the mean revenues in 2010 and 2020. And please answer the question which year was better for the company, of course, ignoring the problem of changes in the prices level, ignoring the problem of the inflation phenomenon. All right. And we can start the exercise. First step is to compute the mean revenues in 2010 and mean revenues in 2020. We can denote the revenues from 2010 using the symbol of XI. We can denote the revenues from 2020 using the symbol of I. Here the population size is equal to 6. As you can see, we have two individual series, or time series, because we have two moments of time and the same objects. So we can talk here about the aponal data actually, yes, because we have one attribute, different objects, and two moments of time, but on the margin. First step is to compute mean value of x and mean value of y. So we have to sum up all the values of that column and divide the sum by the number we have added. Yeah. So in our example, mean revenues in 2010 will be, of course, it's a kind of reminder of the knowledge that we gained earlier. I trust you already know how to do it. And in the nominator we have the sum of all the values of the variable x, 2.1 plus 0.9 plus blah blah blah, 3 dots plus 1.1 divided by 6, of course. And the final result is 11.1 divided by 6, and the average level of the revenues in 2010 is 1.85 billion euros. Yes, this is the interpretation. The average level of the revenues in 2010 in 6 regional branches was equal to 1.85 billion euros. And we can do the same thing with the revenues from 2020, sorry. Here we have 11.1. The sum of that column, the sum of y variable values is 47.6. We divide 47.6 by 6, and we will receive the value of 7.933 billion euros. Yeah, and ignoring the problem of the inflation phenomenon, we see that the mean level of the revenues is higher in 2020 than in 2010. Okay, and in the next step we will try to calculate the variance using both versions of the formula. This version of the formula and this version of the formula. And calculate and interpret standard deviations of the revenues in 2010 and 2020. Okay. First of all, I should write down the formula for variance. Variance of the attribute x values is equal to the sum from I equal 1 up to n of squared deviations of the variable values from their mean divided by n. Okay, but during the calculations of the variance of the revenues from 2020, I will use the second type of the formula. So the variance of attribute y values is the sum from I equal to 1 up to n of yi squared. So this is the average square of the variable y values minus arithmetic mean of the variable y values squared. We have both versions of the formula. I will prejudge which type of the formula is more effective, more easier in the calculation. Okay, so let's start with the first formula. We will try to compute the variance of the revenues in 2010. We will use this kind of formula. As you can see, the first step in the calculation of variance is to compute the deviations. Yeah, deviations, the distances between the xi and x mean. First step, xi minus x mean. Yeah, so we don't care at the moment about the revenues in 2012. We deal only with the values of x. So in the first step, here we have the first difference between xi and x mean. So it means that 2.1 we subtract from the 2.1 the value of 1.85. 1.85. Well, 2.1 minus 1.85 is of course 0.25. This is the first deviation. The second deviation is 0.9 minus 1.85. 0.9 minus 1.85. The second deviation is minus 0.95. Okay, and the next deviations are following. 1.75, 1.35 with a minus sign, 1.05 and minus 0.75. Minus 0.75. Okay, you can check it out that the sum of all deviations are exactly equal to 0. It is consistent with the theory. But we are interested in the squared deviations. So in the next step, we will raise these deviations to the power of 2. Yeah? So here we have, in the next column, we have 0.25 to the power of 2, 0.25. Here we had what? Minus 0.95. And in the first step, we raise 0.25 to the power of 2. 0.25 squared is about 0.063. Yeah. In the second step, we have minus 0.95 squared, and we have here 0.903. Yeah, of course, approximately. And the next values are following: 3.063, 1.823, 1.103, and 0.563. 563. Okay. And now we are going outside the forum, outside the square. So we see that in the next step we need to sum up this column, the sum of the deviations. Yeah, the sum of the squared deviations actually. So hence we have 0.063 plus 0.903 plus 3.063 plus 1.823 plus 1.103 plus 0.563. Yeah, and the partial result is 7.518. Okay. And now we are able to compute the variance of the revenues from 2010. The variance of the values of variable x is equal to, as you can see, the sum from I equal 1 up to n of squared deviations. The sum of squared deviations is 7.518, and we divide this sum by 6, and we have here the value of 1.253 billions euros squared. This is the correct notation of the unit of variance. Billions euros squared. It has no interpretation, so we need to compute the standard deviation of the revenues in 2010. The standard deviation of the revenues is simply the root of the variance. Yeah, in our example we compute the root of 1.253. The root of that amount is about 1.119 billions euros without any squares. Yeah? So this is the standard deviation of the revenues. We know that the mean revenues in 2010 was about 1.85, yeah, and we have different deviations between the values of the revenues and our mean, yeah. The deviations, some of the deviations were positive, some of the deviations were negative, yeah, but you are looking for one synthetic value that express the phenomenon. The phenomenon is called the average deviation of the revenues values from the mean, and the average deviation of the revenues in 2010 is about 1.119. What does it mean? It means that this is the interpretation of standard deviation. In 2010, the revenues deviated from the mean on average approximately by 1.12 billions euros. This is the interpretation of the standard deviation. Yeah, here we have different distances between the arithmetic mean and the values of the variable x. We raise these distances to the power of 2 in order to avoid the problem of negative distances. Yeah, so here we have not only non-negative values, we have computed average squared distance between the variable values and their mean, and after that we back to the right scale to the appropriate unit, because we don't want to interpret billions euros squared. It has no sense, so we should compute the root of that amount, and the final result is around 1.12. So it means that in 2010 the revenues deviated from the mean on average approximately by 1.12 billions euros. Okay, and now I will try to compute the variance and the standard deviation of the revenues from 2020. So now I change the object of my interest from the revenues in 2010 to revenues from the year 2020. Okay, as I said before, I will try to compute the variance using the transform formula, which is the sum from I equal 1 up to n of yi squared values divided by n. So here I need the average square of the variable y values minus mean value squared. Please look inside the formula. In the first stage, we need square the values of the variable y. Squared values of variable y. Here we have the variable y values, so in the first step we raise 2.4 to the power of 2, and the result is 5.76. In the second row I raise 5.6 to the power of 2, and I have here 31.36, and the next values are following: 112.36, 79.21, 92.16, 110.25. Yeah, and after that I need the sum of that column. The sum of that column is 431.1. Yeah, and now on the basis on one column, yeah, here I needed two columns. Now I need only I need one column only in order to compute the variance of attribute y values. The variance of attribute y values is the sum of that column, which is 431.1 divided by 6, because 6 is the population size, minus mean value of y squared. Mean value of y was 7.933 squared. Yeah, and we have here the following relationship: 431.1 divided by 6 is 71.85 minus squared value of 933, squared value of 7.933. Now I'm correct. So the variance of y is approximately equal to 8.918 billions euros squared. This is the variance of the revenues from 2020. Okay, but it is inconvenient in the interpretation. Yeah, I need to come. I need to back to the right scale. I need to compute the root of that value. So after that, definitely I will receive the value of the standard deviation of the revenues. The standard deviation of the revenues from 2012 is the root of variance. In our example, this is the root of 8.918, and this equals to around 2.986 billions euros. Yeah, without any squares. This is the average deviation of the revenues values from the mean in 2012. So we can write it down. In 2020, average deviation of the revenues values from their mean was, or is, because it's the current year, is around 2.99 billions euros. Yes, please write it down because it's very important. This is the interpretation of the measure. So in 2010, average deviation of the revenues values from the mean is around, or was around, yes, it sounds better. In 2020, average deviation of the revenues values from the mean was around 2.99 billions euros. Yeah? Okay. And the next question is how to compare the dispersion of the revenues between 2010 and 2020. We can't use here the absolute measures, yeah, because in 2010 we have observed the mean value at the level of 1.85 billions euros. In 2010 we observed much greater typical value of considered phenomenon equal to 7.933 billions euros. Yes, we have different levels of considered phenomenon, so we are not able to compare these two absolute amounts. We should use here the relative measures. All right, let's move on to the last command. Compare the results from 2010 and 2020. Which year, 2010 or 2020, is characterized by higher dispersion of the revenues in group of 6 regional branches. What do we know? We know the typical levels of considered phenomenon, the revenues, in 2010 and in 2020. We have computed the average deviation of the revenues values in 2010 and 2020 from the mean, and we see that the average deviation of the revenues values in 2010 was 1.119 billions euros, and the average deviation of the revenues values from their mean is about 2.986 billions euros. Let's try to answer this question from the viewpoint of absolute measure of dispersion. Standard deviation is one of the absolute measure of dispersion. We can perceive that the dispersion of the revenues, the average deviation of the revenues values in 2020 is significantly higher than the average deviation of the revenues values from 2010 year. Yeah? It's almost 3 times higher. So we could say that here we are dealing with the higher dispersion. But wait a second. Look at the typical levels of considered phenomenon. Here we have in 2010 significantly lower typical level of the considered phenomenon of the revenues. Yeah. So in the situation where we deal with the large differences in the average level of the same variable, we should relate the average deviation around the mean to the level of the mean value of considered phenomenon. So we should, in other words, we should compute the coefficient, should relate the average deviation to its mean value. We should compute a ratio between the average deviation and average level of considered phenomenon, and we will try to answer the question, what percentage of the mean is the average deviation? Yeah? So, in order to answer this question, we need to learn more about the relative measures. In order to better understand the problem, please imagine the following situation. I'm an investor and I invest my money in two shares. Share A and share B. Of course, share A and share B are listed in the capital stock market, and I know that share A is characterized by the average price at the level of $2, and I also know that the average, based on historical data, the average price of share B is established at the level of $100. Yeah, it's possible, of course. I have also computed the average deviation of the price of share A and the average deviation of the price from its mean for share B. And I have received the following information. I know that the average deviation of the price can be treated as the risk associated with the trading shares. Yeah. Here we have the risk at the level of $1. This is the average deviation of the price of share A, and here the average deviation of the price of share B is the same, $1. Standard deviation equal to $1, standard deviation equal to $1. So, does it mean the risk associated with the trading both shares are the same? The dispersion of the values are the same, the risk is the same if I talk about the share A and share B? Of course not, because here the average deviation in relation to its mean value is higher in this situation than in this situation. Yeah, because here the average deviation represents 50% of the mean level. Yeah. Here, the average deviation of the price represents only 1% of the mean level of considered phenomenon. Yeah. So here we are talking about much higher risk. Yeah. If you look at share A, then the risk connected with the trade of share B. So it is why we need to learn more about relative measures. Fine. Let me say a few words about the coefficient of variation, an example of the relative measures of dispersion. Coefficient of variation is the main classical relative measure of dispersion. It can be denoted by the symbol of capital V with F as subscript, which indicates the measure that have been used in the construction of this relative measure of dispersion. This is a kind of ratio, a ratio between the average deviation of the variable values and the mean value of the variable values. So we divide the standard deviation by arithmetic mean. So we are able to answer the question what percentage of mean is represented by the standard deviation. Is represented by the standard deviation. So, for example, if our coefficient of variation is equal to 30% or 0.3, because this measure has no unit, yeah? If something is expressed in kilometers, yeah, and the variable x is expressed, for example, in kilometers, so standard deviation will be expressed in kilometers, and arithmetic mean will be expressed in kilometers as well. Yeah. So we can remove the unit from this measure, so coefficient of variation has no unit. How to interpret that value? It means that standard deviation represents 30% of the arithmetic mean. Yeah? Standard deviation of average deviation, deviations around the mean, represents about 30% of mean. And the next property is coefficient of variation is computable, of course, in the situation when mean value is different from 0, because as you know, we can't divide by 0. And the sign of coefficient of variation depends on the sign of standard deviation and mean, of course, because this is the ratio. Coefficient of variation can take the real numbers, so it can be both positive or negative. It can also take the 0 value. Coefficient of variation will be positive if standard deviation is positive and our arithmetic mean is positive. It is obvious. Coefficient of variation will be negative if standard deviation is positive, of course, because standard deviation can take only non-negative values, and arithmetic mean will be negative. Yeah. Here we have the unique situation where arithmetic mean is approaching to 0. Here, arithmetic mean is approaching 0 from the right side by positive numbers. So if we divide by ever smaller and smaller numbers, yes, which are positive by positive gives us a positive value, but of course it also means that we multiply the constant standard deviation by ever larger numbers. So coefficient of variation is approaching to plus infinity here. Yeah? So it's not a good idea to compute the coefficient of variation if arithmetic mean is approaching to 0. Of course, we can also meet the situation in which arithmetic mean is approaching to 0 from the left side by through negative numbers. Yeah, so we divide the constant by ever smaller and smaller negative numbers. Yeah, so it means that therefore we multiply the constant by ever larger and larger negative numbers. Yeah, so here we our coefficient of variation is approaching to minus infinity. Yeah, remember that if we meet that situation, we shouldn't use this measure in the analysis of the dispersion in our data sets. Other properties of coefficient of variation. The closer, here we have the coefficient of variation values, and the closer the coefficient of variation values are to 0, yeah, the smaller dispersion we have. Smaller dispersion here and here. All right, and the farther if we farther and farther from 0, we have greater dispersion. Closer to 0, smaller dispersion. Farther from 0, the greater dispersion we have. Here we have the unique situation where we have lack of dispersion, or no dispersion, no spread. Every value are each of values every value is the same. Alright, and at the end I must stress that some statisticians propose here the following example of the interpretation of coefficient of variation. It means that if our coefficient of variation is not greater than 20% or 0.2, we are talking about the low variability of variables values. Yeah, after that we have moderate variability from 20 up to 40% and so on. If we have coefficient of variation higher than 1.5 or 150%, we are talking about the extreme variability. Yeah, here we have, for example, my hand is representing the typical average value of considered phenomenon, and my right hand is representing the average deviation. So here we have small coefficient of variation, low variability of variables values, but here I'm presenting the high variability of the values of considered phenomenon. All right. And finally, we are able to answer the last question from the task 1, please compare the results from 2010 and 2020. Which year is characterized by higher dispersion of the revenues in group of 6 regular branches? So now we are able to compute coefficient of variation of the revenues for 2010 and 2020 year. Coefficient of variation, or maybe VSX, is equal to SX divided by X mean. So here we divide the standard deviation 1.119 by mean value 1.85, and the final result is about 0.605. So it means that average deviation of the revenues values represents around 61% of the arithmetic mean. Yeah, it's very important information. And here we have VSY is a ratio between standard deviation of the revenues from 2020 divided by the mean value of the revenues from 2020 year, and the final result is 2.986 divided by 7.933, and the final result is 0.376. Yeah, and as you can see, we can be surprised, yeah, because standard deviation is higher in 2020 year, but in the relative terms, if we take into our consideration the mean level, the average level of considered phenomenon, the revenues, we are 100% sure that the dispersion of the revenues was significantly higher in 2010. Yes, because coefficient of variation of the revenues from 2010 is higher than analogous coefficient of variation for 2020 year. So the answer is 2010 is the year which is characterized by higher dispersion of the revenues values. Yes, in absolute terms, if we don't take into our consideration the mean, the average level of considered variable, the conclusion is different, yeah? But we must remember, always, yes, this is very important, always, in the situation where we have huge differences between the typical levels of considered phenomenon, yeah? Huge differences in arithmetic mean, we should use coefficient of variation, yeah, because we express the average deviation in relation to the typical average level of considered phenomenon. And as you can see here, in 2010 we are talking about the higher dispersion of the revenues than in 2020 year, and I am 100% sure about this phenomenon.